So today we have with us Dr. Irene Shivaei, giving us a seminar. She's from University of Arizona. I will say something about her background. She did her undergrad in physics at the University of Tehran in Iran. Then, after which she moved to the US, to University of California at Riverside, to do her PhD thesis on the star formation and dust in galaxies at cosmic noon. Most of which was based on observations of her own observations with Keck, with the MOSFIRE instrument, and in collaboration with the MOSDEF collaboration. And after that, in 2017, she moved to the Stewart Observatory in the University of Arizona to work with George Rickey. And soon after, I think in 2018, she was awarded with the Hubble Fellowship, after which she started to work independently, but also as a member of the JWST MIRI and NIRCam science GTO teams. So without anything else, I let Irene to start whenever you are ready.
Thanks, Daniel. Thank you so much for having me today. It's a pleasure. I want to talk about my research, what we know about dust at high redshifts in the distant universe. Dust is this mysterious component of galaxies that we see it everywhere. We see it in the debris and protoplanetary disk, for example, in bird clouds of stars, in the diffuse ISM of nearby galaxies around AGN. And now recently, we have even seen it and observed it in galaxies at very high redshifts. Which means that whether you are interested in physics of star formation and interstellar medium, or you want to design, for example, large galaxy surveys to study galaxy evolution throughout cosmic time, or you are a theorist building galaxy models and simulations, you need to properly take into account the effects of dust. By mass, dust represents only 1% of the interstellar medium. However, it has very important roles in the physics and chemistry of the ISM. It has important roles in star and planet formation. For example, it's a catalyst for formation of certain molecules like H2. It's important in ISM cooling and heating, in ISM gas dynamics, and the list can go on and on. It also significantly shapes our view of galaxies by absorbing the light in UV and optical and re-emitting it at longer infrared wavelengths. And because of that, it hides a significant fraction of star formation in galaxies. And you can see it in these a couple of beautiful pictures from nearby galaxies, that if you look at the galaxies in the infrared, there are these several nodes and regions that are very bright in infrared, showing high activity of star formation that are completely hidden in optical and UV wavelengths. And also, if we look at the spectral energy distribution of the most intense electromagnetic backgrounds in the universe, well, of course, cosmic microwave background is dominating the universe's SED. But after that, from the extragalactic backgrounds, half of it is the energy that comes from dust reprocessed starlight, and the other half is from the starlight. So cosmic infrared background is as you can see, throughout the whole history of the universe, is an important part of the SED of the universe. And now in the past decade or so, with the advancements in the field, particularly the amazing capabilities of facilities like ALMA, we know that dust exists out to the highest redshifts, redshift 8 and 7. There has been galaxies that observed with large amounts of dust. But to to the ballpark, that's it. We have detected dust emission at high redshifts, but we know very little about its nature and its properties at these at high redshift. So this is where my research is focused on. In this talk, I will give introduction about the basics of dust and what we see in galaxies at high redshifts. I will give a very brief insight into a study of typical galaxies at redshift of 2 with ALMA. Then I will show you some recent results on the attenuation, dust attenuation properties and IR emissions, particularly mid-infrared emission of redshift 2 galaxies. And then the future, our plans with James Webb with a focus on the MIRI instrument. So I'm interested to understand more about the nature of dust and how it's related to different phases of the ISM for typical galaxies, typical L-star galaxies during cosmic noon, which is redshift of 1 to 3. Going to the introduction part, however you want to study the galaxies around us, you need some of these parameters that I listed here to understand galaxy formation and evolution. For example, star formation rate of a galaxy, stellar mass, age, star formation history, properties of the stellar population or the ISM gas, or properties of dust inside the galaxies. And to get these, we get these parameters, this information from spectral energy distribution or SED of a galaxy. Now, in the next few slides, I will walk you through with a simple model to better understand different components of the SED of a typical late type galaxy. So we have the emission from stars that are mainly in the UV and optical. They dominate the optical and UV part of the SED of a galaxy. We have the emission of gas, which is composed of the continuum emission at different wavelengths. And then we have very bright emission lines that are spread out at different wavelengths. Here I'm showing three of the hydrogen lines, nebular lines that are coming from the ionized gas around the massive and recently born stars in galaxies. And now there is another complication. If we add dust, dust dominantly attenuates and scatters light in the UV and optical part of the SED and re-emits it at infrared wavelengths. The emission in the mid-infrared is coming from smaller dust grains that are hot at higher temperatures, and the emission at longer infrared wavelengths are coming from larger dust grains that are in thermal equilibrium with their surrounding. So the SED of a galaxy tells us about all these quantities that you might be interested in depending on your science. But to be able to model the SED correctly, we need to take into account the effects of dust, the attenuation in UV and optical, and then the emission in far infrared. For example, for the star formation rate and stellar mass of the galaxies, they can be highly affected. They can be significantly underestimated in normal galaxies, even if we don't take into account the effect of dust attenuation. For the stellar mass, for example, the stellar mass can be underestimated by a factor of 2, and star formation rate can be underestimated by as high as a factor of 10. If the UV to optical or near infrared part of the SED is not properly corrected for the effects of dust attenuation. So to recover, for example, the star formation rate, which is an important quantity of galaxies, we need to either correct the unobscured star formation, unobscured UV and optical lines for dust attenuation, or we need to combine this unobscured fraction, unobscured star formation with the obscured one, which is can be observed at infrared wavelengths. Now, putting these into the context of cosmic star formation activity, here I'm showing the famous Modau and Dickinson plot, cosmic star formation rate density as a function of redshift, which, as we all know, reaches to its peak, the star formation activity in the universe, at around redshift 1 to 3, and then it declines to the current universe. Now, if we separate this diagram into the obscured and unobscured fractions, we see that at least up to redshift of 3 to 4, where we have robust measurements of obscured star formation, dust is very important. In fact, if we look at the star formation rate at redshift of 2 as a function of stellar mass, we see that going to higher and higher stellar masses, a larger fraction of total star formation rate, which is shown with the stars here, is in the obscured phase. So the red diamonds are showing the obscured star formation, blue circles are unobscured, and as you can see, going to higher masses, the fraction of obscured star formation is increasing. And the lower mass regime is where James Webb will complete our view of obscured star formation at these early, in the early universe. Because with the previous facilities like Herschel and Spitzer, we were, as I will talk about it in the rest of the talk, we were mostly limited to the massive end of galaxy evolution. So we know that dust exists. We know that it's an important fraction of star formation in the universe, but there are many questions that are still open in the field. The infrared observations are incomplete. There are very few constraints as we go to higher and higher redshifts on the number counts, and for example, how significant is the fraction, is the obscured star formation from different galaxy populations as we go to high redshifts. We know very little about the properties of warm and cold dust for typical galaxies at redshift above 1. Most of our studies, I'm showing here 3 examples that look at the properties of dust. For example, dust temperature, are limited to Lurgs and U-Lurgs, these massive dusty galaxies at high redshifts. And we have very little, almost no information for the typical and low mass galaxies at high redshifts. And then the same thing for the attenuation properties, the UV and optical star formation rates, or any other parameter that you derive from rest frame UV and optical spectra of the galaxies are not accurate enough for low mass galaxies at redshift above 1. And here I'm showing a few discrepancies that we get if we use different diagnostics for star formation rate at low masses. The different diagnostics do not agree. Or in the bottom plot, for example, I'm showing that if we use different attenuation curves to correct the UV inferred star formation rates, we get systematically different results. And there are very little constraints on how we should treat the attenuation correction for UV and optical properties. Now, this list can go on and on. But an important era to address these questions and build up the steps to basically understand dust at even higher redshifts, like reionization era galaxies, is the epoch of cosmic star, peak epoch of cosmic star formation activity, or cosmic noon, a redshift of 1 to 3. This is when galaxies were at the most active. They were assembling most of their stellar mass, and most of the star formation rate is in the obscured phase, as we saw in the previous slides at these redshifts. So we need to focus on these redshifts and learn about the properties of dust during this era. And luckily, this redshift is an optimal, is very optimal to trace the main dust signatures across the wavelength. With our ground-based optical telescopes and as well as Hubble, we can look at the absorption and scattering properties, the rest frame UV and optical light of galaxies at redshift 1 to 3. The mid-IR emission of these galaxies can be revealed by Spitzer. And as we go to higher wavelengths, we have Herschel and ALMA to trace the thermal dust emission of these galaxies. And with James Webb in the horizon, now is the time to really take full advantage of our current facilities to get prepared to study dust with James Webb, hopefully in near future. So I will first talk a little bit about, I briefly will introduce our survey with ALMA to look at the thermal dust emission of typical galaxies at these redshifts. However, I won't go into any details. So if you have questions, please feel free to reach out to me after the talk. Using with ALMA Herschel, we have a good understanding of the behavior of cold dust emission, the far infrared emission of infrared bright dusty star-forming galaxies at redshift greater than 1. Here I'm showing a compilation of individual IR observations of ULIRCs at redshift of 1.5 to 4. The publication is from 2018. Up to that time, it was a complete compilation of whatever existed in the literature for these ULIRC galaxies at these redshifts. And as you can see, it's very well fit with a locally calibrated LIRC template. The behavior is well predicted by these locally calibrated templates. However, if we go to a little bit fainter galaxies, lower masses and lower metallicity galaxies, all we have are stacks in image stacks of Spitzer. This is the MIPS 24 micron data and Herschel data. And as an example here, I'm fitting 3 different templates of low metallicity local galaxies to these 3 data points. And as you can see, they predict very different far infrared emission by about 10, an order of magnitude different far infrared emission. And this can be only probed by ALMA. So this was the idea of our ALMA survey to select for a very carefully selected sample of redshift 2 galaxies that span a wide range in metallicity and mass. We asked for ALMA band 6 continuum observations to put constraints on the far infrared emission of these galaxies that will provide better which eventually we want to provide better far infrared templates that span a range of metallicity at high redshifts. And using these well-calibrated templates, we would put good constraints on the dust mass of these galaxies, estimating dust masses in a regime that has never been explored before. So the color points are data from existing studies, and the green box is where this survey is probing in terms of dust and in terms of stellar masses. So this is, to my knowledge, the first time that we are going to these low masses. This is a targeted survey specifically to look at typical galaxies at redshift of 2. So there has been many advantages. There has been many advancements of ALMA. ALMA has made a huge impact, really, on our understanding towards dusty star-forming galaxies at a redshift of 2. However, there are some difficulties with ALMA. Here, I'm showing a typical SED of a redshift 2 galaxy, and the symbols show detection limits at 3 sigma level for different instruments. As you can see, for example, aspects or goods ALMA surveys, they do reach down to very high sensitivities. However, the difficulty with ALMA is its very small field of view. In order to reach to statistically large samples of galaxies, it's almost very difficult, impossible with ALMA, because it requires a lot of time. And then, as you can see, with Herschel, for example, the PAX instruments, they're not sensitive enough. They're not sensitive enough to detect typical galaxies at redshift of 2. Maybe in the future, with the Origins telescope, in the next 2-3 decades, we will get a better handle on the far infrared emission of these galaxies. But until then, it seems like we should rely on the optical and mid-infrared data, where we can get individual detections for our galaxies to better understand the properties of dust. And particularly with James Webb, we will be able to reach down to fainter low mass galaxies at these redshifts with the MIRI instrument. So that's why I will focus on some of our recent results on the attenuation and mid-infrared properties of redshift 2 galaxies. And then I will talk a little bit about our plan with MIRI for these sorts of galaxies with MIRI and James Webb. Okay, now the first part, the UV and optical attenuation and mid-infrared emission at redshift of 2. The attenuation curve of a galaxy, as we know, it shows the amount of dust attenuation as a function of wavelength, which is higher at shorter wavelengths. For a simple geometry of a screen of dust in front of the stars, which I'm showing on the left, the attenuation curve determines the shape of the observed spectrum, which means that by knowing the attenuation curve of a galaxy, we can correct the observations to recover its intrinsic emission. However, the problem is that we don't really know which attenuation curve should be applied to different types of galaxies that we observe at high redshifts. And here I'm showing 3 most commonly used attenuation curves. And you can see, so the SMC is in orange, the solid line, the Calzetti starburst curve is in dark red, and then the Milky Way is in the dotted line. And as you can see, for example, if we want to derive properties based on the UV light, there's a large discrepancy between these 3 commonly used attenuation curves. And the differences are mainly in the slope of the attenuation curve, such that the SMC shows a very steep UV slope, while the Milky Way and Calzetti curves have a shallower slope. And also the existence and strength of the UV extinction bump, which is this broad, prominent feature centered at 2175 angstrom that is observed in the Milky Way curve, but it's very weak or almost absent in the SMC and has not been detected in the starburst Calzetti curve at all. Now, going back to what I was telling you in the beginning of the talk, that we derive a lot of properties of galaxies from SEDs. Here, as an example, I'm showing galaxy properties that are inferred from SED fitting for a sample of 1,500 galaxies at redshift 1 to 3. And all the assumptions in these SED fittings are the same, except for the attenuation curve that is assumed. The blue histograms shows the results from an assumption of the SMC steep attenuation curve. And the orange is assuming the Calzetti attenuation curve, which is shallower significantly than the SMC. And as you can see, by just assuming a different curve, we get systematically different results in the star formation rate of the galaxy, in the predicted total dust attenuation, AOV, and also in the age of the galaxy. Stellar mass for this sample is more or less robust because it's controlled by the longer wavelength emissions for the IRAC data in this case. And it's not really that much affected by the UV slope of the attenuation curve. But all the other parameters are highly affected, which underlines the importance of the assumption of the attenuation curve for these sort of studies. And even at higher redshift, it becomes even more important because with our current observatories, as we go to higher and higher redshifts, the only light that we see is rest frame UV. So on the left, I'm showing SED of a galaxy from UV to mid-infrared. And on the right, these boxes show which part of the SED we can observe at different redshifts with the ground-based near-infrared instruments. As an example here, I'm showing the Mossfire instrument on Keck, but we have other similar instruments, on, for example, on VLT or other telescopes. And at redshift greater than 4, as you can see, all that is observed is rest frame UV. With our ground-based optical instruments like MUSE and VLT, it's even more restricted to rest frame UV. Even with HST WIFC3 that goes a little bit to longer wavelengths, again, we are limited to rest frame UV emission of these galaxies. With NIRCam and NIRSPEC on JWST, we will get a little bit more to the optical, but still this range is highly affected by the dust attenuation, and proper care needs to be done to correct these rest frame UV and optical lights for the attenuation. Now, despite its importance, there are a lot of variations in the shape of the attenuation curve at these redshifts in the literature, which, as I demonstrated before, mostly the variations are in the slope and whether or not this UV extinction bump exists at high redshifts. And I would like to categorize the origin of these differences into two main categories. The first one is the geometry of dust with respect to stars can affect the shape of the attenuation curve. So for example, if you have a shell of dust around your emitting sources, around your stars, or if you have a homogeneous mixture of dust and stars, or a clumpy mixture of dust with respect to stars, the shape of your attenuation curve, the slope and the strength of the UV extinction bump changes. Now, keep in mind that this is the x-axis here is 1 over lambda. So this is UV. And as you can see, these different geometries are changing the slope of the attenuation curve. But we see the same effect if we change the composition and size distribution of dust grains. Different combination of small dust grains or silicate versus carbon-based dust grains can result in the same differences or in same changes in the slope of the attenuation curve and the strength of the UV extinction bump. So these two effects are really entangled, which means that the attenuation curve of galaxies encodes very interesting and important information about the geometry of dust and also properties of dust grains in galaxies. Now, most studies in the literature, usually they focus on the radiative transfer effects, which is the geometry, mainly the geometry effect. But what I am interested is to find a way to control for these effects such that I can learn a little bit more about the properties of dust grains in these galaxies. So basically, what I did was, in short, the goal was to derive the attenuation curve for a sample of galaxies that are controlled in their dust optical depth, because the dust optical depth is basically the radiative transfer effects, and galaxies with different optical depth can result into very different attenuation curve shapes, which is just the different geometry effect. So I controlled the sample in dust optical depth, but keep the sample different in their gas phase metallicity, which I assumed can be a proxy for the properties of the small dust grains. So I will now talk a little bit about these two studies to see, which their goal was how the UV attenuation curve changes with metallicity, which is used as a proxy for dust grain properties. In the first study, we derived the attenuation curve of the galaxies, UV to optical attenuation curve. And in the second study, we looked at galaxies as a function of metallicity, where they lie in the famous diagnostic plot of IRX versus UV slope. And I will explain the plot later. So to derive the attenuation curve of a galaxy, the basic idea is that you first start with a sample of galaxies that you assume their intrinsic dust-free SED is similar. And the only thing that is making them look different in the UV and optical part is the amount of dust. Then using an independent indicator of dust, independent of their shape of SED or their photometry, you sort the galaxies to less and more heavily dust obscured bins. So here that independent indicator is the ratio of H alpha, observed H alpha to H beta. The deviation of this ratio from its theoretical value shows the amount of dust in the galaxies, because they're from the same species, from hydrogen, but separated, well separated in wavelength. So any deviation from the theoretical value will tell you about the amount of dust. And as you can see in the right plot, this is the SED of average SED of galaxies in 3 different Balmer optical depth bins, from 0, which is basically dust-free on average, to 0.6. And as you can see, from blue Balmer optical depth of 0 to red, you see the effect of dust attenuating the UV and optical part of the SED. Now, in very simple words, in order to derive the attenuation curve, you will divide these average SEDs, divide these average SEDs to the dust-free intrinsic SED, and normalize it by the difference in their Balmer optical depth to derive the shape of the attenuation curve as a function of wavelength. Now, these sort of studies, this methodology was first fully exploited in the Calzetti et al. 2000 paper. And this methodology has been used for large samples of local galaxies, like SDSS samples of galaxies. But at high redshifts, it becomes more difficult because you need large samples of galaxies with rest frame optical data, particularly H alpha and H beta, to separate them in bins of Balmer optical depth. And this is possible now with our multi-object near-infrared spectrometers on our large 10-meter class telescopes, because time-wise, it's not as consuming as before. And we can also reach down to fainter galaxies and more typical galaxies to get their H alpha and H beta emissions. So the result of this first part of of my talk is mainly based on the MOSDEF survey, which stands for Mossfire Deep Evolution Field. It was a large program with a Mossfire instrument on Keck, about 50 nights of observations. The main goal was to get rest frame optical spectra for about 1,500 galaxies at redshift of 1.5 to 3.8, which is the cosmic noon. And the redshift was particularly selected to be able to capture all the main optical emission lines. For example, here I'm showing the observed spectra of a redshift 2 galaxies, where we have oxygen lines, hydrogen Balmer lines, N2, S2. So in the bottom, you see the extracted 1D spectra, and in the top is the 2D spectrum of these galaxies. And generally, the goal was to use this wealth of optical nebular emission data to study the gas, stars, black hole activity in these galaxies. Now, from this sample, from this large data set, I selected a controlled sample at redshift of 2 that they are The only difference between the two samples is their gas phase metallicity, their oxygen abundance. In the right panel, I'm showing the UV slope versus Balmer optical depth. And you can see that the Balmer optical depth distribution of the red, which is the high metallicity, and the blue, which is the low metallicity sample, are very similar to each other. So by this way, I'm trying to control the optical depth and radiative transfer effect on the attenuation curve. But their metallicities are significantly different from each other. And I have separated these two samples at the oxygen abundance of 8.5, which translates roughly to 0.6 solar metallicity. And if you use a stellar mass metallicity relation, this translates to stellar mass of 10 to 10.4 solar masses. This is just to give you an idea of what kind of galaxies we're talking about. And then I used the methodology that I explained before to derive the attenuation curve for these two samples. And here is the result. For the first time, we are seeing very distinct differences between the attenuation curve of the galaxies as a function of metallicity. So the low metallicity curve that is shown in blue, the solid blue curve, is steeper, is very similar in terms of slope to the SMC curve, which is shown with this dotted yellow line in the background. I mean, it's overlapping, so it might not be very obvious, but it's very similar in terms of slope to the SMC curve. And we couldn't detect significantly any sign of the UV extinction bomb in this curve. On the other hand, the high metallicity curve, which is shown in dark red, in magenta color, has a shallower slope, very similar to the Calzetti curve in terms of the slope. And we significantly detected a bomb with about half the strength of the Milky Way bomb in this curve. So the Milky Way curve is shown with the black curve in the background. And as you can see, we have a bump, but it's a little bit weaker. Now let's take a look closer at these differences to see what we learn about properties of dust in galaxies based on these differences that we observed. So first, the slope. The difference in the slopes is telling us something about possibly the different grain size distribution in these galaxies. The larger fraction of small dust grains can cause a steep rise in the UV attenuation curve. And we do expect to have a larger fraction of small grains in the low metallicity galaxies because they have harder, more intense ionizing radiation, which makes it easier to shatter the large grains to small grains. There's also possibly lower molecular fraction, lower fraction generally of molecular clouds for dust grains to hide in, which makes them again more prone to shatter to smaller dust grains. It can also tell us there are theoretical studies that show different grain compositions. Certain differences in the grain composition can cause a steep UV attenuation curve. It can also be an age dependence. However, we didn't really find a significant sign for the age dependence in these two curves. The bump is also very interesting. The fact that we see the bump in the high metallicity curve, but not in the low metallicity curve, is telling us that the grains that produce the bump are not really present in the low metallicity environment. Now, a candidate that has been suggested in theoretical studies and in lab studies for the bump is the PAH molecules. These are large carbon-based molecules that absorb single UV photons and emit in the mid-infrared. So if these molecules are responsible, they should not be present in the low metallicity galaxies. Now, as I said, they absorb the UV photon and emit in mid-infrared at certain wavelengths. The strongest emission is at 7.7 micron, which can be traced by Spitzer MIPS 24 micron at these redshifts. Now, we tied this result to a study that I led a few years ago that I looked at the mid-infrared emission of the same sample of galaxies as a function of metallicity. So here on the y-axis, I'm showing the PAH intensity, which is observed from Spitzer MIPS 24 micron data as a function of metallicity. And if we look at galaxies separated at the same metallicity limit that we separated them to look at the attenuation curves, we see that at high metallicities, the mid-infrared emission is significantly larger than at low metallicities. This suggests that the PAH molecules are present in the high metallicity environments. They absorb the UV photons, hence we see the UV bump in their attenuation curve, and emit in the mid-infrared. But at low metallicities, they are preferentially destroyed, possibly by the harder and more intense ionizing radiation. And therefore, we don't see the emission, and there is no absorption sign in the attenuation curve either. Now, moving to the second study, I wanted to build on this previous study by incorporating infrared data and look at the infrared emission, directly look at the dust emission of these galaxies. So in order to do that, I want to look at the locus of galaxies in the IRX beta diagram, which is IRX is the ratio of IR luminosity to observe the UV luminosity as a function of a UV continuum slope, which is sensitive to the amount of dust attenuation, dust reddening. So IRX beta diagram was originally developed to assist high redshift observations that only have access to rest frame UV, as I show you in the left panel. By calibrating the UV continuum slope, using the ratio of IR to UV luminosity, basically beta UV continuum slope becomes a very powerful empirical diagnostic for recovering the total attenuation corrected UV luminosity using only rest frame UV observations. So this is the strength of this empirical relation. Now, different attenuation curves have different, occupy different places in the IRX beta diagram. For example, the Calzetti curve with its shallow slope is here, and the steeper SMC curve is here. It is, has this locus in the IRX beta diagram. And I showed as a rainbow color how from a shallow to steep curve, how different places are occupied by galaxies. So again, I used a sample of galaxies with metallicities that are derived from rest frame optical spectra, and I incorporated Herschel and Spitzer data to look at their infrared, total infrared emission and place them in the IRX beta diagram. Now, just to remind you again, this is where the Calzetti shallow curve of Calzetti is. This is where the SMC lies. And here is our result. We see that the galaxies span a full range of attenuation curve slope possibilities, from a shallow Calzetti type curve for galaxies that have the highest metallicity in our sample, all the way to a very steep SMC curve for those that have the lowest metallicity in the sample, metallicity of about 8.3. So it shows that metallicity is indeed an important factor in the scatter of the IRX beta diagram, which is dominated by the slope of the attenuation curve. We see a correlation with mass as well, but it's much weaker. And I think that it's basically because mass and metallicity are correlated with each other. Now, to go back to the first question that I brought up in the talk, that how accurately can we derive star formation rate from rest frame UV? We tested our metallicity dependent attenuation curves and derived the SED star formation rates using those, compared them with independently derived H alpha star formation rates. And you can see the result in the blue histogram that is centered around the unity ratio, which shows that using these metallicity dependent attenuation curves, we are very well recovering the star formation rates. And also, if we look at the IR luminosity, predicted IR luminosities of these galaxies using a metallicity dependent curve, they match very well with the observed IR luminosity. And just as a practice, if we predict the IR luminosities using a constant curve, for example, a Calzitti curve for all types of galaxies, or an SMC curve for all types of galaxies, we see that we get systematically incorrect results. Now, in the next few minutes, I want to just briefly talk about a little bit about the future with James Webb and what we are planning to do, particularly with the MIRI instrument that covers observed 5 to 28 micron wavelength. So 5 to 28 micron for redshift 1 to 2 galaxy is the mid-infrared aromatic spectra of galaxies. Which, as I mentioned briefly before, is commonly attributed to the emission from the PAH molecules. These PAH molecules absorb single UV photon, get transiently heated to very high temperatures, and emit light at certain wavelengths. The strongest one is at 7.7 micron, which was observed easily with the Spitzer 24 micron. And looking at the state-of-the-art studies from Spitzer 24 micron at these redshifts, it advanced our knowledge about obscured star formation to a great degree. However, those studies, because of the limited sensitivity of MIPS, they're all limited to very bright, dusty IR galaxies at redshift greater than 1. In fact, if we look at the what Spitzer could do, that MIPS 24 micron could do for us, for redshift 2 galaxies, on the y-axis is the Spitzer emission, strength of the Spitzer 24 micron flux, basically, as a function of stellar mass. And in this bottom part of the plot, you can see the detection fraction of these galaxies. At masses below 10 to 10, which is a very typical mass for galaxies at redshift of 2, the detection fractions for individual galaxies is less than 10%. Now, this is where James Webb will become very crucial to advance our knowledge about obscured star formation at high redshifts, because it has a much higher sensitivity. Here I'm showing 3 sigma limits for 1 hour integrations of Spitzer and MIRI. And as you can see, it can reach to easily to typical galaxies and below at redshift of 2. It has higher resolution, which means that with longer integrations, we can even reach to lower fluxes. There is no it's not confusion limited, which Spitzer 24 micron was. But also it means that we can actually look at individual galaxies at these redshifts. Just think about how much we learned from Spitzer MIPS 24 micron about obscured star formation at high redshift. And this is the PSF we were working with compared to their image in optical. And with MIRI, we will be able to actually look at individually these galaxies. So I think it will be very exciting and new era. But also the other advantage is that MIRI has multiple bands. So far, in terms of photometry, we only had one band of 24 micron in Spitzer, but with MIRI, we have 8 bands, and we can look at different PAH features in the mid-infrared spectra of high redshift galaxies. So our plan with the US MIRI GTO is to trace the mid-infrared emission of galaxies at redshift 1 to 2. We are looking at good south field in 15 pointings, observing the whole field in all 8 bands of MIRI. And the idea is that with all these 8 bands, we can get a very low resolution spectra, like RF5, from the low resolution mid-IR spectra of the galaxies. And with the sensitivity that we are going for, we will get to the star formation rate of about 10 solar masses per year with signal to noise of 10 at redshift of 2, which means that we can easily observe lower star formation rates at still detected signal to noise ratios. And with the stacking techniques, we can really reach down to very low masses and faint galaxies. this is at least an order of magnitude deeper than what we have in the deepest images of Spitzer MIPS. And then using this wealth of information from different bands of MIRI, we can study properties of PEH molecules. So for example, their size and charge state, but also looking at the physical conditions of the ISM. For example, the radiation field that these PEHs are exposed to. And we also have some plans to get follow-up observations with near spec for our galaxies to get the optical emission lines and get the ISM ionized gas properties in the ISM of these galaxies. So in summary, I think I mainly was trying to show that multi-wavelength spectroscopic and photometric surveys of galaxies in AGN at cosmic noon are really the next frontier for comprehensive galaxy evolution studies. And we are looking in the future at ELTs to better probe the rest frame UV and optical of these galaxies. We will have James Webb, and with ALMA, we can look at the far infrared emission of these galaxies. And I think with that, I will just leave you with this summary points and gladly take questions now.
Thank you very much, Irene. Very nice talk.
Thank you.
Let's see, anyone has any questions for Irene? Please go ahead, raise your hands, or maybe directly speak. Gina?
Hi, yeah, it was a great talk, Irene, thank you. I wanted to ask, so you showed the metallicity dependent attenuation curves that you derived, and on average, you found a good correspondence with, the existing literature for the low metallicity and the high metallicity part. I was wondering if you could use the spread and not the mean curve to answer questions like, is the UV bump of the Milky Way a typical size and stuff like that? And the second question is, will you use the polarization of the ALMA measurements?
So the second question I will answer first because it's shorter. No, I haven't thought about it, and I don't know how easy that would be for the faint galaxies in the at these redshifts. But I will be definitely interested to hear more from experts on that. The first part about the spread, with this small sample size, it was really not just binning them in 2 metallicity bins was the best that we could do. You need a much larger sample size to actually look at the galaxies in between and see if you see, like, you just demonstrate the transition, not 2 bimodal curves. But in terms of how typical the bump of Milky Way is, from different studies and other things that we are looking at, for example, rest frame UV spectra of these galaxies, the Milky Way bump is not really typical. It's stronger than what we see at high redshifts. It's not 0, which was for a long time the consensus that it doesn't exist at high redshifts. I don't think that's the case. It does exist, but it's weaker. However, we have, when we talk about the attenuation or the basically extinction curve of Milky Way, we're talking about line of sight extinction curve. It's a very simple geometry of for Milky Way, SMC, and LMC. This is the case. It's a very simple geometry. You have the star and you have a screen of dust in front of them, and you measure the extinction curve. However, for the galaxies, like the study that I showed here, we're talking about coupling this extinction curve with the geometry effect in the galaxy. And no matter what you do, if you just mix up your stars and dust with each other and no longer have this simple geometry of dust and a screen of stars and a screen of dust in front of them, you suppress the strength of the UV extinction bump. So my point is that the bump that we see at high redshifts is a lower limit on the actual bump that exists in the extinction curve of these high redshift galaxies.
Thanks, that was very clear.
Any other questions for Irene? Kostas first, and then Vasilis.
Hi, thank you for the nice presentation. So my question is, you showed before that a good agreement between the transformation rates retrieved through SCPs and H alpha. So in that case, what was the extinction indicator that you used in order to correct for the alpha attenuation extinction? And also, if you consider using different extinction indicators, for example, between the Balmer decrement or the IRX, and if you find differences between these measurements, for example.
Yeah, that's a very good point. So for the H alpha, H beta star formation rate that I showed, I usually assume a Milky Way curve, and that's because first is because of the simple geometry that I mentioned before, that for the nebular regions, we think that simple geometry is the best approximation. But also recently we had a study that looked at the nebular attenuation curve, specifically in that wavelength range, and it's very similar to the Milky Way for nebular lines. That's the first short answer to the question. But if you look at it more carefully, the differences in the attenuation curves at that wavelength regime of optical, the wavelength of H alpha and H beta, are not that different. Looking at different curves, the SMC, Calzetti, Milky Way curves, they're very similar in there. And assuming a different curve to correct the H alpha line for the dust attenuation doesn't translate to large systematic uncertainties in the total star formation rate, which is not the case for the rest frame UV. Rest frame UV, the attenuation curves change more drastically.
Thank you.
Maybe Vasilis, you had a question?
Great talk, Irene, thanks. I had a couple of questions, actually. One is a bit philosophical, right? Why do we want to study about metallicity effects in high-Z systems, right? When we know from simulations that the ISM is very rapidly polluted anyway, at least to a moderate metallicity. And also it's very difficult to handle geometry issues, as you argued, given the fact that these are more gas-rich systems, so you have extended star formation throughout their disks, and similar luminosity objects do not have the same distribution of their main power source, even if it is star formation. That is one. And the other, it's, maybe I noted it, I don't know if I noted correctly, you suggest that one of your conclusions is that you can, the UV derived SFR, when you take the proper extinction curve, you seem to be able to recover that correctly. That was one of your conclusions, right?
Yes.
But I presume this is for lower luminosity, lower mass galaxies, which are not necessarily the more luminous ones, right? And in those, you are optically thin in H alpha. Because if you are optically thick in H alpha, then it would be hard to do anyway, right? So it's only this type of systems.
Yes.
Okay.
So in both of my cases, I would say I don't have any optically thick H alpha in this sample, because to start with, these are all main sequence galaxies, and they don't really have any of those starburst beasts or very like sublimiter galaxies or anything. So this, all the results I said for both cases, like the low metallicity and high metallicity as well, these are all optically thin H alpha, I would say.
and their mass is below 10 to the 11, probably, right?
Mostly, yes.
Because it's okay.
Yeah.
So the first one, is it other than the fact that it's exciting to to explore the parameter space, isn't it too hard to answer metallicity, geometry, and all those things?
It is very much entangled, the two, but we not like in all these studies that I show you, we do see a change in whatever property of dust that we look at. For example, the pH emission, we do see a change at around 0.6, 0.5 solar metallicity. We see that something is happening. Now, what is causing that is not a very easy answer. Is it the chemical abundances, which, as you said, it's a little bit hard to believe because they should be very early on. Being the gas the ISM should have been enriched on shorter time scales, but it can be for example, it can be the properties of the ionizing radiation in the ISM that is changing the distribution of dust composition or dust size of the dust grains in the ISM, which does then, if that's the case, it will affect everything that we see in terms of dust, like the far infrared emission would be different. The mid infrared emission would be different. The attenuation curve would be different. So I don't think it's necessarily the oxygen abundance that matters. I think here I'm mainly just using oxygen abundance as a tracer of the ISM condition as a whole that is changing. And the reason I'm doing that is it's easier to get oxygen abundance compared to something like carbon abundance. That would be very difficult. Does that sort of answer?
No, that's fine. Yeah, thank you. Thanks a lot.
Any other question for Irene? If not, I will ask probably the last one. I just because you mentioned that you have an ALMA program, right? And I assume that is for a fraction of these galaxies that you have observed and from which you derive the extinction curves. So I was wondering what is the connection, right? What ALMA will bring to the table that let us, know more about the dust composition, maybe, or properties of dust?
Yeah, actually, let me see if I have a backup slide for the galaxies in ALMA. Actually, I don't, unfortunately. So let me make sure. Yeah, I don't have the backup slide, unfortunately. But I think, so it is a subset of galaxies, and they're carefully selected to span a range of metallicity and mass. Yeah, I wish I had. It's harder to explain. So they're carefully selected to span a range in metallicity and mass. They are not very low star formation though, because it would be it would require very long integration times then with ALMA. And the idea is that to see whether the dust masses in these galaxies, or generally the infrared template of these galaxies, are different from the typical Lyric galaxies at these redshifts. And we do, so the study is actually sort of advanced, so hopefully something will be on archive soon. But what we see is that the very preliminary results. The low metallicity galaxies show a hotter dust, and their IR emission, their total IR template, is wider than the typical Lyric galaxies. at the same redshift, which can be due to multiple things. It can be, one thing can be because we have multiple components of dust emission. So for example, the H2 regions have very hot dust around them, so they're contributing to the emission at shorter wavelengths in the IR template. Or it can be because if you have, for example, more silicate dust, in a galaxy, because of their higher emissivity at wavelengths of around 70 micron, like 50 to 70 micron, they will show a hotter IR emission at those wavelengths. So which makes, again, your SED wider.
Per optical depth, let's say.
Yes. Yeah.
The little dust that you have, it will have higher emissivity, so more luminous, better dust.
Yeah. Yeah, but of course, these two are entangled. So I don't think we will, with this limited data, we will know what is happening. But observationally, what we're seeing is that these low metallicity galaxies have a different IR emission.
Okay.
IR.
Just a little follow-up question, because you say that you selected the galaxies in metallicity and mass. And I remember in one of your slides, I think it was in the IRX beta parameter space, you were explaining the distribution of galaxies based on metallicity, but also you mentioned that you were seeing also a variation in masses, in stellar masses, but it was not as pronounced, right? It was not as clear as the distribution that you were seeing in metallicities. So I was wondering if that is telling you something about the mass metallicity relation evolution with redshift, or is too much reading into it?
So we know about the mass metallicity relation at, so this is first let me show you the plot. So this is the metallicity, top left is the metallicity relation, the change with metallicity that I showed, and this is with mass. So the mass metallicity evolution with redshift, we know that there is an evolution, and it's parameterized. So that's why I'm saying that if we look at that relation, you can easily translate what we see with metallicity to what we see with mass.
Okay.
And I think metallicity is the deriver here, not mass. Well, first of all, because there is a just easier connection from metallicity to dust compared to the total mass of a galaxy and dust. I mean, you can connect them, but I think it's more physical to think about that the chemical abundances are doing something with the dust properties than the total stellar mass of a galaxy. But also, just in terms of the like a mathematical sense, the correlation with mass is much weaker than the correlation with metallicity. Yeah.
Okay. Thank you very much. Unless there are some other questions, I think we are a little bit already over an hour. So thank you again, Irene, for giving this seminar. Very interesting.
Thank you very much. It was great.
Sure. Yes. Thanks for having me.
And we wish you the best.
Thanks. Thank you very much. Have a good evening.
Thank you to you. Bye-bye.
Bye.